We're back, everybody. It's been a long time since I made one of these things, but I noticed I recently passed 6,000 subscribers and I thought I owed it to at least make another tutorial video. I don't have as much time as I used to make these things. I've kind of been working full time lately. But this one I think is really useful because I can't tell you how many times it's come up in my career that I need to be able to read a file specification in a binary file and be able to import it into my software and essentially have it work correctly. So I'm going to walk you guys through what that looks like. It's pretty advanced, but it's something that I feel like a lot of programmers might struggle with, or they always just be like, well, let's use a third-party library to do that. Let's not do that ourselves. And I think that's kind of a sign of, I don't want to say weakness, but it's just a really valuable skill to have. So before I dive in, I'm going to kind of go over the two possible kinds of file formats, at least on a very high level, that you might encounter. Typically when dealing with files and reading them into your software, you'll typically will find that files will either be one of two types, and those two types are either ASCII files, which are essentially, it's a fancy word for text, and binary, which is basically everything else. And everything really fits under these two umbrellas. You can actually kind of think of ASCII as a special case of binary and how we interpret it, but for all general purposes, let's really think of them as being separate. So what do I mean by ASCII versus binary? Well, a lot of file formats, when you try to open them, if you want to essentially see what makes them tick or what's inside of them, if you were to drag those files into a text editor, like this 3D OBJ file here, if what comes up is essentially human readable, that is a really good clue that that's an ASCII file format. So here basically we have readable text, which looks like directives that you can kind of parse in using the using some of the tutorials I've done previously on my channel on how to read and write ASCII files using parsing, right? The numbers are essentially typed out in plain text. They're easily readable. It's very obvious that these 3D vertices in this OBJ file are 6.18, 4.66, -15, so forth. So that's what text looks like. There are tons of different ASCII file formats out there. Some of them are arbitrary or kind of make up their own rules, like this OBJ file. Some of them adhere to existing structures, like JSON, which is its own type of ASCII file format. Specification, XML is another one. HTML is another one. You get the point. The thing that I really want to hit here is that they're human readable, and they depend on converting ASCII to other types of data, whether you're parsing a string or parsing a number and so forth. The other type of file format is called binary, which is, you can think of a lower level, more optimized or efficient file format. If you were to take a file format that's binary and drag it into a text editor, essentially you're going to see complete junk. You're going to see characters that cannot be readily converted to ASCII that are going to come up as question marks. You're going to see things that literally look like Greek. You'll see a little bit of text here and there, but basically you're going to see garbled junk. That's a real clue that what you're looking at is a binary file format. So real quickly, before I go over how one might read a binary file format, let's go over the reasons, or I guess I could say the strong suits of one versus the other. So why would you use binary when ASCII is clearly more readable? Binary file format types are extremely optimized, or much faster compared to ASCII. There's two ways I can explain that. I can explain that in time and in space. So in time, think about a really, really large number that's, say, 4 billion. This is 10 characters. So focusing just on the time aspect of it, the CPU, if it was to read this number in and convert it to a 4-byte integer, or unsigned int, would have to actually process and convert each and every one of these digits into base 10 and then convert that to a number. In other words, the CPU has to waste time trying to figure out what this number is and eventually convert it into something. It has to parse it. It's extremely fast in the grand scheme of things, but as you start to get hundreds and thousands and millions of numbers, the time it takes to parse those really adds up. So it's much slower than if this number was represented in pure binary, in which case we could literally just copy it right into memory, assuming the number was in the same format and generated by the same CPU type. That goes into things like endianness, which I'm not going to cover in this video, but I might later. So that's time. Space. Well, as you can see, I just counted out 10 characters here, and assuming you have 1 character per byte in ASCII encoding, that's 10 bytes. An unsigned 32-bit integer only takes up 4 bytes. So we've basically wasted 6 bytes to store the same number. And this, as you get into millions of numbers, blows up like crazy. 3D artists, if you've ever dealt with OBJ files before and you see them taking up 300 megabytes, which is ridiculous, and then convert them into something else like 3D Studio Max or whatever, and it takes up only like 2 megabytes, that kind of explains why this problem is here. So there are massive advantages for using binary file formats for data, especially large amounts of data compared to ASCII. So, how the heck do you read a binary file then? Well, there's a couple of ways that you can first think about a binary file. It's useful to install a hex editor on your machine so that you can at least look at a file without it coming up completely like junk. So if I were to drag this LAS file into my hex editor here, I would basically get a really convenient series of hexadecimal representations, 2 at a time, of each byte in the file. This allows me to essentially do Swiss Army knife things like select the range of bytes and see what their integer equivalents are and so forth. It's just worth mentioning. I'm not going to use it too much for this tutorial, but it's a way for you to at least kind of get an idea of what a binary file looks like. Not the text on the right, but all of this stuff here in the middle. This is what the hexadecimal representation of a binary file looks like. Now, in this particular case, the file that we are working with here is an LAS file. So what I did was I looked up the LAS file for the version of I looked up the LAS specification for the version of the file that I know we have. Every time you're reading a binary file, you will essentially need to come across or obtain the specification for that file, which tells you how to read it. So the first thing you want to do when you find a file spec is you want to find the header specification, which tells you essentially what the header block looks like and how the file essentially starts. This looks a little scary at first, but don't worry about it too much. I'm going to explain. The very first thing that most binary file formats start with is something called magic, or a file signature. Essentially what this is a series of bytes, typically 4 bytes long, which are kind of, you can think of them as ASCII letters, which tell you what this file is. So if you try to open the file and you don't see the signature, you know something's wrong, you got the wrong file type. And as you can see when I go back to my hex editor, indeed this file does start with LASF. So at least I know I'm working with the right thing and I'm not going to read a bunch of code and screw around and have the wrong file spec. The rest of this stuff involves basically what we need to do is declare a struct which contains the exact same layout of all the data types given here so that we can read the struct in directly from the file and then read information about the file through the header. So what I'm going to do right now is quickly type out this struct and then I'm going to explain. So the most important way that you can get started as far as reading a file header, a file header in, is to generally take the header block and turn it into a struct. The struct essentially allows you to lay out all of the data in the header block in a contiguous fashion so that you can then read that in from the file. So let's do that real quick. So I've basically gone to the header file here, and I'm going to create an inner struct, which is a struct inside my point cloud class called header. And then we're going to declare all these things inside here as quick as I can. Okay. So as you can see here, basically, I've used the more specific C++11 types that tell me exactly how many bits the fields are taking up, which are, in my opinion, a little nicer to use than the ones where you kind of have to guess. So every time I see unsigned short, I'm using a uint16t. Every time I see unsigned long, which it tells me 4 bytes, I'm using uint32. Every time I see character, I'm just straight up using a character, unless I think uint8t, which has the exact same size as character, is appropriate. I typically use characters for letters and uint8t when I know it's just a number. And where it calls for double, which is an 8-byte double precision floating point number, I just use double. So that's essentially what the header looks like as a struct. Now the important thing to remember about a struct in C++ is that the memory layout is essentially contiguous, so that if I were to take this structure and copy it around, or copy it, say, from a file, it would essentially come out exactly the same way. So essentially what happened here was something I really, really wanted to avoid because I wanted to keep this tutorial simple, but that never works out. It has to do with struct packing and byte alignment between members of a struct. The reason why this didn't come into my mind is because most file format specifications take into account how annoying it is to deal with it and will typically keep their boundaries between variables on 4-byte alignment boundaries or 8-byte alignment boundaries, depending on 64 or 32-bit. I kind of saw that there might be a problem with things like arrays of 5 and like 2 bytes packed back to back. The long and skinny of this, what it means is if you declare a bunch of variables back to back in a struct, to make things more efficient for the CPU, the compiler will pad and put filler bytes between variables to make sure that all the variables that are 16 and 32-bit and so forth will always start on an even word boundary, which basically means is the CPU will always have the memory address of these numbers starting on a multiple of 4 or a multiple of 8. This makes it a giant pain in the ass, though, when you need these things to be tightly packed together to conform to, say, reading from a file specification. Again, I really didn't want to get into this, but I was left with no choice because it doesn't work unless I do it. So what I had to do was insert this special stupid thing here, which is basically a way for the compiler that I'm using, LLVM, to say that this damn struct is to be tightly packed together. This will only work for Mac. Or not Mac, LLVM. If I was compiling on Windows, I would have to do something like Pragma Pack 1, I think, inside Visual Studio to make it do it for that as well. But basically, without this, the structure will not be tightly packed. So I'll show you guys how to read from a file real quickly. I have a point cloud class here, which takes an argument to the path of the point file or the LAS file, and then calls read, which I'm then going to go ahead and populate with some code to actually read the file in. So we're going to go ahead and use fstreams to read this file in. For those that have seen my code about parsing files in ASCII and essentially reading them in from my Adventure R tutorial series, this is going to look really similar in the beginning, but then I'm going to kind of go in a little different direction. The way that you work with fstreams is you first include the header, and then you declare one, in this case ifstream for input, and then we give it the path to the file we want to read, and this is important. Second argument, we have to say this is a binary read mode for this file. If you leave this out, you can actually end up with some errors in your file reading. So it's important to say that we're reading this file in a binary mode. Once we do that, we make sure that the file open succeeded, and if it didn't, we throw an exception that basically says we can't find shit, and we're good. So at this point, the file is open, and we need to actually start reading it. So what I'm going to do here is declare an instance of our header, which I've done here, just locally, and then I'm going to go ahead and call the read function inf.read. And what this does is it takes a pointer to some data, which we're giving it the address of the header. So we're basically telling it to fill in the header by reference, and then we're giving it the number of bytes we're going to read from the file. So all read does is basically takes a pointer to some block of memory, reads the second argument number of bytes, and then essentially that's it. So by passing the address of header in, we're basically telling it to read directly into our header struct. And that's how you essentially read a header in binary. This cast to char here is just to get C++ to shut the hell up about this thing not being a pointer to char, which is essentially the old-fashioned C++ way of saying that there's a pointer to some amount of bytes. Once we do that, we want to verify a couple things. First, I want to make sure the header, version major and version minor, comes up exactly as 1.2, so we know we have the right version of the file spec. And I want to look at what the header is saying the size of the header is, and make sure that this is exactly equal to our reported size of the header. If it's not, then I screwed something up when I typed out the header, and it would be bad. So I'm going to do that, put a breakpoint after, and run it, and make sure we're on the right track. So now when I do this and print out the header, I will actually see that most of the information in the file is sane and makes sense. In other words, the number of points in the file is not billions, but instead a very digestible 575,000. The scale is reasonable per the XYZ. The extrema, the minimum and maximum Y's are offline. So we're going to go ahead and move on here and essentially digest more of this data. For this particular file format, I'm just going to throw some asserts in here. So one very important thing inside the header that kind of tells us what we need as far as reading the points is the point data offset, which is the byte offset from the start of the file where the point records actually begin, and the point data record format, which tells us the format of the individual point records. Now I kind of scouted out ahead here, and when I printed out and saw that in this particular case, the record format for this particular file is 1, which basically means I'm going to disregard all the other types. Again, for this tutorial, for the sake of learning, I'm not going to go too far into the different types of ways to support every possible kind of LAS file. This is just an example, so I'm going to read this particular file. So in this case, I'm going to look up what this thing says regarding format ID, which is here, and then I'm going to scout ahead in the file and look and see what it says format number 1 is. So format number 1, according to this, is a structure that kind of looks like this. I'm not even going to give this thing a chance to give me a problem. I'm going to, again, do tightly packed alignment. And I'm going to type in and follow all of the stuff inside the file. So we have X, Y, Z, which are integers, surprisingly, instead of floating points. So these are uint32t's. We have intensity. We have a return number, which has to do with the actual scanning of the points, which is kind of interesting, which, of course, is 3 bits, which is fantastic. So let's see if these add up to 8. 1, 2, 3, 4, 5, 6, 7, 8. They do. So I'm just going to call this all flags, because I'm actually not going to really care about this stuff. We have classification. We have a scan angle rank, which I'm not 100% sure what that is, but at least it's another uint8t. We have user data, which is something I really don't care about. We have a point source ID, which is another thing I don't care about. And we have GPS time. And just double check this, long. Okay. So we're going to go ahead and call this point record 1 since it's conforming to format 1. And we are going to then read in, or essentially seek to the part of the file where it says the points are and start reading those in. I'm going to throw another assertion in here and make sure that we don't proceed if the record format is not 1. That could cause some problems. All right, so how do we essentially go to the part of the file where it says these things start, which essentially is the offset? It's actually quite simple. Just going to double check. It says offset the point data. So what we're going to do is we're going to do inf.seekg. And what this does is seeks from the beginning of the file the number of bytes you specify, which is the point data offset. From this point, assuming this succeeds, we can just start reading the record. So I'm going to start a for loop here. I is 0. I is less than header number of points. I++, and we're going to read one of these records in at a time. We're going to need data to actually store these point records. So what I'm going to do in this case is create, I'm going to create this inside the function itself. Right here, create a pointer, set it equal to points, and we're going to create header, number of points, number of these things. And just to be safe, I'm going to delete it, which gives the memory back when I'm done before the function returns. This allows us to then do read our stuff. So the idea is we do read, we give it a pointer, which I'm going to come back to in a second, and we're going to read in point records at a time. Now, what are we passing for this pointer? Well, we could do the address of points sub I, but if we want to be a little bit more clever, pointer arithmetic allows us to just do points plus I, which will essentially move the pointer by its size every increment. So this is a way of us to quickly get the address of the ith number or ith element in the array. And again, this thing is going to bitch because we're not giving it a pointer to char, so we just cast that. This is the point where we really want to make sure nothing went wrong during the read, so I'm going to throw another assertion in here. Well, I might just say if is good, which is, if the file is not good, meaning it encountered an error during any of those reads, then we're going to throw a runtime error and say reading ate shit, which is a way for us to know that something went wrong. I'm going to go ahead and throw a breakpoint in here and see if we were at least able to read some of the points. If it doesn't crash, we're on the right track. So let's see what points sub-0 looks like. Everything here looks pretty good. Let's jump ahead about 100, 200. I'd say we're in pretty good shape here. So what we're going to do here is we're going to essentially convert these to something that OpenGL can digest. There's a number of ways we can do that. I think the simplest way for me to just get moving here would be to use a C++ vector and have a vector of float 3s, which we're going to go ahead and define a struct for right now. This is kind of hacky, but this is easier for me to do than to do 3 floats at a time, which can kind of be confusing with the math. So that's a vector of float 3s, and this is going to be the point data, or the vertices that we're actually going to use to render this thing in 3D. We're not going to directly hand this ugly struct to OpenGL and expect it to understand what this stuff is. We're going to convert it to floats, which then we're going to give to OpenGL to render. And really quickly, I'm going to create a method to actually get the data out of this class, which is a pointer to float3, get verts data. And what this thing is going to do is return the data stored inside of the vector. Clean up here. Okay. One more thing we're actually going to need to do here is to get back get verts count, which is the number of points stored in the vertex array, which OpenGL is going to need. So, okay. Now I've written those routines, this would be the time in the code to actually go ahead and start converting the points into the data. One thing that's readily apparent to me is that I only need one of these points at a time. So instead of creating this stupid pointer and this memory, or instead of creating this block to memory every time, it would make more sense to read one of these at a time and then just convert them live and then store the result in the vector. Get out of here. Okay. So instead of me doing all this fancy stuff I did before, I'm just going to go ahead and do point. That's the address of point. Read it in, and then convert it, which will be pretty simple because I have all the information I need. God, I wish this thing would shut the hell up. Okay. I have all the information I need to convert the information from these integers that it's giving me per point to the scaled floats. The quickest way I can think of doing that would be to take the scale factor that has been provided for me and just multiply the points. So in other words, float 3v equals point x times header scale x. I just know this thing's going to complain, so convert the float. And then essentially do this 3 times. Taking care to make sure that I do not get my x, y's, and z's mixed up like I like to do so much. Then I can take our vector, verts, push back the result into the vector. If you guys haven't already realized, this video is pretty much covering the culmination of just about, well, not all, but many of the tutorials leading up to this point. It's pretty advanced, but hopefully you guys are able to follow through. And if it's a little rough on you, there's nothing wrong with going back to the old videos or, slowing this down and going over this multiple times. I do apologize. I tend to go a little fast. It's because I finished work today and I'm kind of in that mode instead of, my normal slow tutorial mode. Hopefully this comes out well. I'm going to go ahead here and see out the whole results here, just so I can see what these points look like before I bother giving them to OpenGL. Because what would be the point if they're not going to render correctly? So at that point, we're pretty much done. This covers how to read LiDAR points from a binary file by following the file specification. As you can see, the points are printing out there, and I have the data read into the class such that I can actually pass it into OpenGL routines and then convert the data into OpenGL format so I can render the points in 3D. So basically what you're seeing here is I wrote a clever function that just takes the points and centers them so that they're not completely in real-world meters so that OpenGL can actually see them. And then I pass that data into OpenGL through the normal OpenGL channels, and I'm able to actually visualize the point in 3D. As you can see here, the data is turned on its side, and that's simply because in OpenGL, Y is considered up, where in a lot of scientific engineering world applications, Z is considered up. So later on, you're going to see some footage of the points where I rotate Z to be facing up, or I rotate Y to be facing up, so you can actually see the points scaled better. But that pretty much covers the whole tutorial, so I hope it was useful for you guys. I hit a lot of roadblocks and hiccups along the way, but the end result looks pretty cool. So that's it.